These
like
are
blooming,
so
like
these are
flowers.
yeah. Well, that's just his name, but it's
Ah, it's a name.
uh, so it's bloomsticks.
La UNA es uno de los pilares de la educación costarricense. Hemos evolucionado acorde a los tiempos y demanda de la sociedad. Trabajamos en investigación, extensión, innovación y docencia gracias a la inversión que realiza la sociedad costarricense junto con el esfuerzo de profesores y administrativos en beneficio de los estudiantes. En busca de preparar a los estudiantes para los desafíos de su vida profesional, donde poder conectar los conocimientos básicos con el desarrollo actual y futuro, sin olvidar nuestra relación con las comunidades, es fundamental para poder desempeñarnos en la cuarta y quinta revolución industriales. Es aquí donde no podemos olvidar que la UNA, tal y como nos lo recuerda uno de sus fundadores, don Francisco Morales Hernández, nace de la escuela normal y la escuela normal superior, por lo que la educación de excelencia es una prioridad para nosotros. En búsqueda de excelencia es que gracias a la colaboración de muchas personas de la UNA y del Instituto Tecnológico de Massachusetts, hoy contamos con la visita del doctor Rea Laví. El doctor Rea Laví tiene un bachillerato en psicología y un bachillerato en biología de la Universidad de Tel Aviv, una maestría en educación de la Escuela de Educación de la Universidad Bar Ilan y su doctorado lo realizó en la Facultad de Educación en Ciencia y Tecnología del Instituto Tecnológico de Israel, del Tecnión. Actualmente el doctor Laví se encuentra trabajando en el Departamento de Aeronáutica y Aeroespacial del Instituto Tecnológico de Massachusetts y nos va a compartir esta mañana todo el trabajo que está haciendo y esto espero que nos ayude a seguir impulsando la docencia desde la Universidad Nacional. Con ustedes, el doctor Rea Laví.
Muchas gracias, professor. Thank you so much to the National University of Costa Rica for inviting me. Thank you all for coming. And before I start, I'd just like to mention if anything I'm saying is not clear, then please just put your hand up. And if I can't see that you're putting your hand up, then make a noise. And I will stop to make sure that what I'm saying and what is on the slide is clear to everyone. If you have, not questions just to clarify, but bigger questions, questions to expand on what I'm talking about and so on, then I ask, if possible, that you just wait until I'm done with the talk. Maybe you can write down your question. It is easier to do it that way. But if you are not sure, then just put your hand up. It's really important for me that what I'm saying is clear to everyone. So the topic of what I wanted to talk about today is using active learning to prepare students for addressing unstructured problems in the real world. Now, this presentation will be made available to everybody. So if you want to write something down, you're welcome to, but you don't have to. And I will explain what all these different terms mean. What do I mean by active learning? What do I mean by unstructured problems? And so on. So a little bit of context for our talk. Some of you may have heard this term. Has anyone heard this term, VUCA? Just put your hand up if you have at some point heard this term. Oh, yeah, sure. I'll use the clicker if I need to. Thank you. So, it's a laser pointer. Very nice. Okay, I think for now I don't need it, but thank you. So this term VUCA has been around for about 20 years or so, and the idea is that the world we live in today, more or less since the internet has become worldwide, and everyone has smartphones and so on, has become very different to what it has been previously. And this has many effects on all of our lives and the world, but of course also on education. So the world today is volatile, which means things change very quickly and they change from 0 to 100 and then back again. It's uncertain. There's a lot of uncertainty. And you see our lovely friend Corona over there as an example. And the world is, of course, very complex and ambiguous. I'd just like to ask a very quick question for you to think about. Let's say you ask somebody 20 years ago, how real to you is your digital persona? So your persona on LinkedIn or Facebook or Instagram or whatever. And you ask people the same question today. How many hours a day do you spend as your digital persona, or how real is it to you? This is just one example. So is this the real me? Maybe 20 years ago, people would say, no, that's not the real me. Maybe today they'll have a different answer. I'm not sure. I don't research the topic, but I think it's an example that everyone can relate to. So what is the motivation for this talk? Why is it at all important to hear about active learning and unstructured problems? So I try to summarize it here. Firstly, there is an increased demand by industry and by governments for engineers, but not just engineers. This is, of course, my main topic of research is engineers, but also scientists and people who are not scientists or engineers, just employees in general, that are able to address unstructured problems. So the skills that go into this, I'll go into this a bit more in other slides, but for example, being able to identify problems, being creative, being a systems thinker, these are becoming more and more important. But the level of academic achievement rarely corresponds to the ability of students to address these kind of problems. So a student can be excellent academically and receive very high grades. Doesn't mean they are very good at addressing unstructured problems in the real world. And it doesn't mean they're not good, but there is simply, it's not that there is no correlation, but the correlation is very low. Now, studies have shown us, not just in engineering, also in science education, that active learning methods can develop these skills, can help develop these skills. And there are actually a lot more studies in science education than in engineering education, because this topic is a little bit more neglected, especially in the undergraduate level. So if you go to Google Scholar, for example, you search for undergraduate biology, active learning, you will find many studies. Biology is a good example, actually, where they do a lot of this. Less so in physics, but biology certainly a lot. And finally, education bodies, international, national bodies, have recognized that they need to develop these skills in students. So it's not new. This is not just me coming here and saying it. There are many papers about this going back even 20 years, which means you need to make changes to curriculum and to pedagogy. So changes to what we are teaching and also to how we are teaching. And there is a slide at the end with all the references if you want to go and read more. So the content of the presentation, at first I'll give a bit, really tiny bit of like theory, education theory, and then we'll go directly to the topic. I'll talk about what is active learning, what are unstructured problems. Then I'll get to the application of this in terms of pedagogy, like how do you teach this stuff? How do you develop these skills in students? And I will show you examples from my experience and other people's experience. So problem structuring, creative problem solving, and systems thinking. These are all skills that are helpful with addressing unstructured problems. They're not the only skills that are required, but these are the ones that I research and teach, so I can talk about them. And finally, we'll have questions and answers as well. So a bit of context. So there's this term called higher order thinking, or higher order thinking skills. So in general, what do we mean when we say that? We say that, firstly, they are non-algorithmic, which means it's not about I'm given a recipe, I'm given an algorithm, I'm given a specific clear method from A to Z, and I learn how to apply it. It's a different approach. And some problems can be solved with an algorithm that we already know. Some problems cannot be solved with an algorithm we already know. We may need to come up with an algorithm or come up with a different approach. So that's one way of looking at higher order thinking, what it is. The second one is that it generates multiple solutions. So again, unlike an algorithm, which we know when it's right, we know when the solution is correct, and there may be very few or even just one optimal solution. This is not the case for higher order thinking. We're looking to generate multiple solutions, multiple alternatives. And finally, higher order thinking involves uncertainty. It involves the application of multiple criteria for evaluating what is a good solution. It involves reflection by the student or by the person who is trying to solve the problem or by the team. And it involves self-regulation. So I need to regulate myself, how long I'm spending on each part of the problem, how well did I do, how well did this solution do, what in my thinking led me to this solution or to another solution, and so on. So here is quite a long list of different higher order thinking skills. And again, there are studies that kind of try and classify these. So you can see some of the skills that I spoke about, right? Like problem solving, creative thinking, systemic thinking or systems thinking. I use the word systemic thinking because that's the word these authors used. Systems thinking is more commonly used. But as you can see, all of these actually make up higher order thinking skills. So this is one way of looking at higher order thinking skills. Another way is if anybody is an education student or somebody who studied education, they've heard of Bloom's taxonomy. This is a very basic taxonomy we all learn about. It goes back decades, and the idea of higher order thinking is that we are looking at the words at the top, right? So we're looking at, in terms of Bloom, we're looking at analysis, synthesis, and evaluation, and less on knowledge, comprehension, application. Now, of course, we cannot have these without these. If the student doesn't understand, they don't have the knowledge, they haven't done any application, it's going to be very hard for them to be able to do the other things. But the idea is that to approach unstructured problems and to engage in active learning, we need to get students to do this stuff. And there's another way of thinking about this. Anderson's taxonomy, which is based on Bloom, he took what were nouns and he turned them into verbs, into actions. I personally think that's a better way of thinking about it, but of course it's academia, we can argue about everything and it's fine. But it's the same idea, essentially. So that's it in terms of the context that I want to provide you with. And now we can go directly to the topic. And I'd just like to mention, originally the talk was supposed to be, 45 minutes and 15 minutes Q&A. I will try and stick to that, but I might go a few minutes over. I hope that's okay. So, what are necessary components for active learning? And you can look at this kind of as a definition. I don't like to give a definition because, again, it's academia and we can argue definitions forever. But it's useful to know, is what I'm doing active learning, right? Is it actually active learning? Is it going to help develop these skills? So what you want to have, use of higher order thinking. And I just showed you a very long list. So something on that list needs to appear in that activity. There needs to be teamwork, and if not teamwork, then some meaningful interaction between students, right? So not a lecture, for example, a typical lecture doesn't count as active learning, because a lecture may develop the critical thinking of students. For example, if students ask questions and the lecturer asks questions and they have a debate or something, or they talk about topics and they criticize things, but there is no meaningful interaction normally between students in a lecture, right? Maybe there's a bit of a back and forth. And finally, individual reflection on the learning. So the students need to be given an opportunity, either in speaking or in writing, to reflect. What have I learned? How does it connect to other things I've learned? What did I understand well? Or what did I find difficult? How does it relate to other things I understand well or find difficult, and so on and so forth. So these are necessary components for active learning. And there are different types of active learning. And these are not all the types of active learning. And you can see there is no reference here, right? Which means I made this up, because there is actually arguments about what do we mean exactly by problem-based and so on. I don't want to get into that. What I want to do is provide you with some useful framework for thinking about this and what might be suitable for you. So you can see I used two axes. One axis is how structured is the problem that you're giving to students? How structured is the prompt? And I'll explain in a little bit exactly what I mean by structured, but for now I can just say it means how clear is it? Or how much work do the students need to do to figure out what the task is actually is? So That's one axis. And of course, the more well-structured the problem is, the less autonomy the learner has, because you are giving them a very specific task. And another one is how long it takes, right? So it can take maybe weeks. We can do it in weeks if it's case-based learning. But if it's a project, try and do a project with students in 2 weeks or 3 weeks. It's not a good idea. They're not going to get very far. They're going to feel frustrated, and so on. And another thing is it more about applying knowledge they already have, or is it more about acquiring or creating new knowledge? It doesn't mean that it's 100% like this and 100% like this, but it's where the focus is. So what do I mean by how structured the problem is? So this is a spectrum of something called problem structuredness. It's a very interesting paper. It's called The Theory of Education of Problem Solving, Jonathan. Again, there's a slide at the end with everything. But Jonathan gave this spectrum to understand different types of problems, and he came up with this term called structuredness. I find it very useful. So the most ill-structured problems are dilemmas. So I don't know about your country, but in the US, for example, this is what's called a wedge issue. So a wedge issue is an issue where you have about 50% of people think one thing and 50% think pretty much the opposite. And this is what elections are decided on. So these are good examples for dilemmas. So in America, for example, they have gun rights. If people should be allowed to carry personal weapons, and if so, what kind of weapons, and so on. And again, opinions aside, this is certainly an issue where you have a big group that thinks one thing very much one way, and a big group that thinks one thing very much another way. And I'm sure in Costa Rica you have some issues like this as well. So this is an example of a dilemma, right? So these are the most unstructured problems. So what does this mean in this little drawing I made? The initial state or the problem space is very unclear. It's very vague. It's very uncertain. And we have to actually begin exploring the problem to begin to form it into something that we can understand. What is it exactly that we're trying to solve? And the same goes for the solutions. So what does a good solution look like? How do we judge what a good solution is? Do we care about cost? Do we care about safety? Do we care about accessibility, and so on and so forth? It's not clear from the outset. It's not a textbook problem. And the same goes for how to solve the problem. It's not clear how to solve the problem. We don't have an algorithm. We don't have a specific method. We may have some ideas, but again, we need to explore, go through a process, iterative, right? We need to go back and forth, and we need to negotiate with the stakeholders, and we need to look at the real world and apply things and try things out in order to understand what we can actually do. The opposite is true of well-structured problems. Well-structured problems, we know exactly what the initial state is, we know exactly what a good solution looks like, and we know what the approach is. So I'll give you an example, Sudoku. Anyone know Sudoku, or a crossword puzzle? So they can be very difficult, right? Sudoku can be super difficult. Crossword puzzle can be super, it doesn't mean they're easy problems, but there is only one way to solve a Sudoku in terms of what you're actually supposed to do. You're supposed to put numbers in the squares, and you're supposed to, according to what you put in one square, figure out what the other squares are. And yes, there are different strategies, but ultimately in computer science speak, it is a theoretically solvable problem, right? There's a very limited problem space, essentially. So these are what well-structured problems are. So here's an example of a case-based learning course. And this is a course that I teach. I am now teaching it for 3 years at MIT. It's a first-year course. It's called Neat Ways of Thinking. Neat is just the program that I work for, New Engineering Education Transformation. It's an undergraduate program. So as you can see, the way this course works, we go from unstructured or ill-structured problems. It's the same thing. We go from well-structured problems to oh, I can see that it's not showing the entire. Over there, it's showing it, just in case you're missing something. So we start with well-structured problems, and we work the way up to ill-structured or unstructured, because it's difficult to start with unstructured problems, especially with younger students. It becomes frustrating and confusing to them, because they're used to 12 or 13 years of structured problems, right? They're used to 12 or 13 years of sitting at school and receiving textbook problems, mostly. So we start with, for example, formulate a search strategy for a mini bot, like a little robot, like a little car, that's looking for balls on a grid. So, and they use Scratch. Scratch is like a no-code kind of program that they can use. And it's basically, we're teaching them algorithmic thinking, right? That's what we're teaching them. And they get feedback, and then they do it again, all the way to conceive and design a method to help first-year students at MIT choose the right major for them. So at MIT, students choose their major. They choose basically the focus of their degree at the end of the first year. So they have an entire year, well, not really an entire year, but like a semester and a half to decide what they want to study, physics or biology or electrical engineering or whatever. So the last assignment that they do here, they use algorithmic thinking, creative thinking, and systems thinking to come up with a method or a tool to choose the right major for them. This is an unstructured problem, because how do you decide what do you mean by a right major? Does it mean what's going to make me the most money? Does it mean what I'm going to like doing? Does it mean maybe what my family wants me to do, right? So it's an unstructured problem. And we end with like what is a well-structured problem, but it's very fun just to do something with their hands, casting and molding, which is important. I don't know if you know MIT, the motto is mens et manus, which means mind and hand. So we want to introduce that as well. But the general idea of my course is not just that they do all this stuff. I want them to actually understand what it means that there are different types of problems, and what do I mean by a well-structured problem? What do I mean by non-structured? And we talk about that in the class. So this is an example of case-based. Every one of these is just 2 weeks. And I'm joined by a different instructor. So the instructor is the subject matter expert, right? Autonomous machines instructor, climate and sustainability, bioengineering, digital cities, and so on. And here are the assignments in my course. So I have what I call preparation assignments. And these are more the lower levels of the taxonomy. These are knowledge and comprehension and a bit of application, so that they are prepared to do proper application in the class. So most of the work is done, students work together, either in the class or outside of the class, because it's just 1 hour a week and then 2 hours outside of class. And you see almost all of it is as a team. And then finally we have reflection. We have 5 reflection assignments throughout the course. They're reflecting on creative thinking, they're reflecting on systems thinking, they're reflecting on algorithmic thinking, they're reflecting on unstructured problems. And I also see how they reflect differently at the start of the course, the middle of the course, the end of the course, and so on. So this is an example of an active learning course, the type of case-based learning. And it took me a long time to get it to where I'm happy with it. It's not the first. The first time was, I think it was pretty good. It was during COVID. It was on Zoom, and now it's in person. And it was actually harder for me. The hardest part for me was when we came back in person, was to take this course and make it into in-person. That was actually the hardest part, and that's a different presentation. So now, how do you use active learning to teach the structuring of problems? So this is an example of a course. I taught this in the spring of 2022. The first third of the semester, 4 or 5 weeks, was just about structuring the problem. So this is not like the course I just showed you, where every 2 weeks was a different problem. There's just one problem, and it's a real-world problem, and I'll show it in the next slide. And students, undergraduate students, not just first year in this case, undergraduate students from different years, tackled this one problem throughout the course. We spent the first third just structuring the problem. The students were not happy at first. They wanted to get to 3D printing and fabricating and trying things out and doing creative ideas. Why do we have to spend so much time on modeling the problem and all this? But I think it's very important. And I think it's often neglected, especially in undergraduate education, really putting emphasis on how important it is to structure a problem or design it. So there are basically 5 steps. And I have a full article I wrote about this. You can read it if you want. But first, you just give a brief description of the problem. Usually it comes from the customer or from the person, the stakeholder, the person who's suffering from the problem. Then you inquire into the problem by answering these 5 questions. And I'll explain what this means. You essentially write a report or a case description with references. You research the problem. Then you model the problem as a conceptual hierarchy. So you create some kind of a conceptual model. So if any of you know concept maps, concept map is like the simplest tool. I actually use something a bit more advanced. But using concept maps is also fine. It can also be very helpful. But this one allows me to do it in a hierarchy, which I'll show what I mean. Then you extract leverage points. So This is the power of systems thinking, by the way. This is really using systems thinking, this model and extract hierarchically. You can find points deep within the model, like processes and objects and functions, that if you just change them, if you put some money or effort to change them, you can make a big difference to the overall problem. Because the analytical approach says, let's take this huge problem, let's break it down into tiny parts and try and solve each one. That's unfortunately not really possible for reasons of time and resources, and also because different components of the problem affect each other. So systems thinking is very helpful here. And finally, you create a paragraph that answers the 5 W's from here with the leverage points you found. And this is what I call the intelligent 14-year-old. So you create a paragraph that describes the core of the problem you're trying to solve. You've structured the problem into a paragraph that an intelligent 14-year-old can understand. So it doesn't have technical terms or anything like that. All that stuff, all the complicated stuff, all the details, all the justifications are found here and here. That's where we as a team know that we're basing this off of knowledge, we're basing this off of prior literature, off of our own research, but this is something you can communicate with everyone who are involved with the problem. All the stakeholders, everyone who might want to invest in your project and so on. So let's go to describe, the first step. This was given to me in an email by an MIT professor who was actually dealing with this problem as part of a project at MIT. So the course I was teaching was not set out to solve the entire project, but he gave me this one challenge. Okay? So the city of Ulaanbaatar is the capital city of Mongolia. It's the coldest capital city in the world, and it's also the most polluted because they use coal to heat up their homes. And a little bit like your situation here, you're in kind of a valley, they're also in a valley. But imagine if you had the winter minus 40, minus 20. By the way, minus 40 Fahrenheit Celsius is the same. That's how cold it is. So, and imagine that you all use coal, and there were 1 million people. So you can imagine the amount of pollution and how terrible it is. So at MIT, they're working on a solution, an engineering solution, which is called molten salt. It's a thermal battery. It's about the size of a shoebox. It's encased in stainless steel. And there is a salt in there that is being heated up to very, very high. So this is hotter than, where does it say it? 400 degrees. It should say somewhere 400 degrees centigrade Celsius. That is hotter than boiling oil, okay? And it weighs quite a lot. But it can give off heat. And what the idea is we use the waste heat from the coal power plant. So there's just waste. We're not using it. We heat up the bricks, and then we transport them. This is the plan, right? This is the vision. It doesn't exist right now. But the brick exists, and it's been tested in the lab. But there is a problem. Okay, how do we get it into these traditional huts, gers? About 300,000 people live in them in the city of Ulaanbaatar. How do we get them in there? So you can imagine all kinds of problems, all kinds of risks, right, that could arise from transporting this and getting this into people's houses and so on. So we were just asked to focus on, okay, let's say it's in a truck and it's near the neighborhood. Now, how do we get it into all these houses? So we are not worrying about all the other problems, right, in this course. So the scope is very important. How are you going to scope your problem? So the next step was inquire. Now you can see this is just a description, like it's limited, maybe it's biased, it doesn't include a lot of details, but we have to start from somewhere, right, when you're trying to structure an unstructured problem. So inquire, what we do is we answer these 5 questions. And what we did was, and really my students, created a 6 or 7 page report answering each one of these questions with images, with references, with statistics, and so on. And you'll see in a little bit a few of the answers. So the next step is to model. And this is a very powerful tool. It's called Object Process Methodology. It's from Model-Based Systems Engineering. It's used at MIT. It's used by Airbus, if you know the airplane company. It's used by a bunch of companies. It's a very useful tool, I find, for education, for kind of an advanced concept map. And this is what my students created with my facilitation. So I'm not going to go through the whole model. It's just to show you that basically everything here is made up of processes, a process, this oval blue thing, and objects, which are these green things. And then we can go down a level you see that this process that was here is broken down into 3 processes that happen one after the other. And each one of these processes affects the objects that we saw in the top level. And then there was even another level for each one of these, right? So you're creating a conceptual hierarchy. Unlike concept maps, conceptual models are constructed using a formal graphical language. So we know what all of these links and everything here means. We're not making any of this up. And they distinguish different types of concepts. Okay, so we have things like creating objects, consuming objects, changing states of objects. We have whole-part relationships. We have exhibitory properties. We have types and subtypes, and so on and so forth. And there is sentences that are created automatically as we create these diagrams. So again, I don't want to go into this. It's just the general idea here is that we can look at the problem, inquire, create a case description, then based on that, create a hierarchy of concepts of what happens with this problem, what are the different interactions, what are the different objects, how do they interact, how do they relate to each other. So this is what my students did. This is directly taken from their final presentation. They looked at this model that I just showed you, and there were more levels to it, deeper levels, and they found that these are the leverage points. Like, these are the points that you need to focus on because there is no good solution for them right now, and we really need to focus on them, put a lot of time and effort into them, and if we manage to solve them, then we would go a very, very long way towards solving the problem. So you need to lift the brick from the vehicle, you need to get it through the fence, you need to pass the threshold of the ger. By the way, you're not allowed to touch the door frame for cultural reasons, so you can't just drag the brick, because that would be one idea. You can't do that. And you have to replace the cold brick with a hot one. Okay. So finally, based on the case description that they wrote, and based on the model and the points and so on, this is the statement they came up with. During colder months, especially October to April, if gers can be heated with molten salt bricks, this would keep the people in there warm, and it would not cause them the damage that coal causes them, right? Heart disease and cancer and all these horrible things, which is great. But there is currently no viable method to transport these bricks from the truck in the Ger district, where all these huts are, to the stove. The main obstacle are what we saw before. There's these 4 obstacles. And this is basically the problem we are trying to solve. So, except maybe for the word ger, which you wouldn't know what it means maybe if I didn't explain it to you. Except for that word, I think everything here is pretty simple. It's not super complicated. It's not super technical. There's a lot of physics that goes into this, right? You want to look at thermodynamics. There's a lot of logistics that goes into this. There's physiology, because if you want people to be carrying these bricks all day as delivery people, and ergonomics, right? Human engineering for humans. There's a lot that goes into this, right? But this is just you can show this to the person who lives in Ulaanbaatar, right? You can show this in Mongolia, and they would understand what you're trying to do. So, how did this happen in this course, right? What kind of assignments did I give students? So they had application, like you remember the case-based learning. Case-based learning course was all about applying. And here, there were certainly a lot of those, because I wanted them to learn different methods. How do you write a case description? How do you create a model? How do you look for extraction points? How do you come up with ideas, right? That was the second part of the course. They needed to review. They had 2 design reviews, because it's a project-based, right? They had a whole semester. Presentation, just one at the end. Learning vignette, these are kind of like the preparation assignments. Like they watch the video, answer some questions about different ways of thinking. Reflection again. And because the teamwork was very important, they're one team working on one real-world problem, I wanted them to reflect on their work as a team. So these are the assignments. So that's it in terms of how to structure a problem, how to use active learning, right? So higher order thinking, teamwork, and reflection. Now we are going to how to use active learning to foster creative problem solving. So a creative idea, again, academia, lots of arguments, what do we mean by creativity? But if you look at over 100 definitions in the literature, 2 properties that come up the most, 2 attributes is a creative idea is novel and useful. So it has to be something new or rare, but it also has to be effective. So this is an example of a problem statement that I gave to my students in the fall of 2020 in my remote course, which I was telling you about, the case-based learning course. And the first time I ever taught in my life on Zoom, I taught this course, and it was a brand new course. It was quite challenging. This is the problem statement I gave them. I just showed you before a problem statement. This is another one. So campus shutdowns because of pandemic. Many undergraduate students had to participate in synchronous online classes, right? Zoom class. But in this medium on Zoom, wordless speech, which is a large part of communication, is limited because you can't see most of the body of the person. And also, you are in 2D, the resolution is not like in real life. So a lot of body language and wordless speech and things like that just get lost. And this decreases the quality of learning. So what do we do about this? So I'm going to jump directly to examples of ideas that students gave. We went through a whole process, right, which I'm not going to go through here, but just to explain what I mean by novel and what I mean by useful. So I would claim that the most creative idea was this one, because it was both novel and useful. So create a larger list of emojis. By the way, in 2020, Zoom had a lot less emojis. Now Zoom has a few more, right? But they had very, very little. So obviously, Zoom understood that they need to do this, right? More diverse range of emotions, the ability to display to individual participant, the host, the person speaking. So this doesn't exist today in Zoom, which is interesting. Like, I can send an emoji just to the speaker. Or, you know, yes, you can send a private message, but just send an emoji to the speaker or to specific participants and so on. I would claim that the least creative idea, the least novel and the least useful, students should sit farther from their cameras to allow more body language to show through. Well, yes, we could sit farther back, but then it would be harder to hear and so on and so forth, right? So this is, again, we could argue this as well, right? Like some people may place this differently, but I just wanted to show you an example for how, what I mean when I say novel or I mean a useful idea and so on and so forth. So in this way, this is how we can assess, right? If we ask students to come up with ideas, like one very easy way, we can do a 0, 1, or 2, and we can say, okay, is it novel relative to the ideas of other students in the class? That's relative novelty, but also relative to publicly available ideas. Like, are there products like this? Are there patent applications like this? And so on and so forth. And that's a bit less relative. That's a little bit more objective. In terms of usefulness, that does require expertise, right? If I need to decide whether a product or an idea or a solution is useful, or if an experimental design for scientific research is useful, I need to be an expert. And the idea of assessment really is not to be summative, is not to give a grade, is to be formative, is to see, okay, maybe the student has more trouble coming up with novel ideas, but they're very good at useful ideas, so we should put more emphasis into this or more emphasis into that. So this is just a way of assessment. And those of you who will come to the workshop tomorrow today and tomorrow will do a bit more practice on this. And now I want to quickly provide you with a mechanism for creative thinking, for creative ideation, to come up with creative ideas. So analogical reasoning is actually the main mechanism. It's the most common way that inventors and scientists come up with the ideas and solutions. So there's two definitions that we need to keep in mind. One is the target problem. That's the problem we want to solve. And that's after we've defined it. It's very important to structure the problem first, okay? Because if you take just an unstructured problem and you try and come up with ideas, you might end up with having to recall your products or getting a lawsuit or, or just not working very well. And the source problem is where we get the analogy from, where we can get the ideas from. So a source problem is similar to the target problem in some ways. It has already been solved to a satisfactory degree, and it can be used as an inspiration for solving the target problem. So we can look for similarities between these two based on attributes, functions, purposes, and so on. So how does this method work in practice? And again, you can go and read about this. I have this in my references, and this is something that is also going to be used in the workshop today and tomorrow. So this is a method that I've developed with a colleague, Dr. Denise Marty from Harvard. And the idea is that first you state the problem. I already showed you how to state the problem. That's the last step of problem structuring that I showed you. Then you find out criteria that are common, usefulness criteria that you use to compare your target, that you use to compare solutions to your target problem. Then you look for a suitable source. You can use YouTube or Wikipedia for this, very, very useful. And then you come up with analogies. And then you can use those analogies to come up with ideas. And I'm actually now looking into ways to use ChatGPT, to use generative AI text, to augment this process. And I'll show you what that looks like. But of course, you don't have to use ChatGPT. You can just do it with human beings, and that's perfectly fine. And also, just a quick word about ChatGPT. I always want the human intelligence to do it first, and then I use ChatGPT to augment. I use ChatGPT to help. I don't use ChatGPT to replace. And I'm not going to go into that now, but I think there's a lot of issues with misuse of ChatGPT. It's so easy. It's so conversational. It sounds so confident. But it can lead you down a very bad way if you just trust it to do everything. And you need domain expertise. You need to know how to structure the prompts for ChatGPT. So speaking of structuring prompts, these are the actual prompts that I use. I'm not going to go through them now, but they're available to you. So to take this process, use it with ChatGPT. You can use it this way. And here's an example. So target. This is the problem statement. I took a case description that I had ready, like a 10-page case description with the who, what, where, when, and why, with references and everything. I fed it into ChatGPT, the free version, by the way. This is all the free version. And I asked it to state the problem in the same way that I ask students. It's exactly the same. All of this is what I ask students to do. And this is the statement it came up with. Okay? I'm not going to go into now whether I think it's a good statement or not. I think it's generally okay. I would improve some things about it, but it's interesting. And I think if you had students do it and then had ChatGPT and had a conversation with students about what ChatGPT did, and maybe they can take some things that ChatGPT did and use it, you know, let's use it as something useful rather than to just replace everything. I think it could be a good thing. Next is criteria. I asked ChatGPT to offer me usefulness criteria. And I think it did a pretty good job, not with all of them, but certainly with some of them. So it came up with these 5. It says, okay, a solution to this, if you want to compare solutions, you need to compare it by how affordable it is, what is the impact on the health of the residents, how accessible it is, how sustainable it is, and how efficient it is. Okay, even if I don't want to use all of this, I think it's a useful input. Next, source. I asked it, come up with source problems, come up with problems that have been solved and that share as many of these criteria with my target problem. Energy poverty, food insecurity, environmental pollution, transportation equity, education equity, and so on. And again, the idea is not just to take what ChatGPT gave you and just trust it blindly, but take this as now a springboard or an idea. Okay, I can go and research more. I can go read up more about these different problems, and let's see what the solutions were to these problems. And finally, I said, okay, take these and come up with analogies for the target problem that would help me think of creative ideas. And it came up with a bunch of analogies for each one of these source problems. Okay? And now I asked it, this is just a bonus, I said, okay, based on the analogies, come up with creative solutions. And I actually asked it to put 2/3 on originality and 1/3 on usefulness. So I wanted to go a little bit wild, right? I don't want it to be too practical. And these are actual ideas it came up with. So we've got creating a Ger district emergent energy co-op. So the idea that people can share the various, not just the bricks, but the various different methods, different energy sources that they use together, right? We can create some kind of a database for them or an app. The Food Oasis Initiative, Pollution Warriors Campaign. So Pollution Warriors Campaign is nothing to do with really with technology so much or engineering. It's more to do with public policy, with public campaign, right? Now, some of the ideas are not great. Like, for example, the Food Oasis didn't really have much to do with the problem. But some of them are actually worth thinking about. So again, I'm not suggesting to just give ChatGPT to do all of this, but I think it is pretty cool. Once you have a structured way, right? This is a very structured method of coming up with analogies. Once you have a structured method that you as the domain expert can understand, then I think you can use ChatGPT very effectively. So again, this is an example of creative problem solving with active learning. So students certainly use their higher order thinking skills. They work in teams to do this. They present their work, they reflect on their work, and so on. And last but not least, using active learning to foster systems thinking. I spoke to Jefferson before. I don't know if he's still here, but I heard that there's a bachelor's in systems engineering here, which is very exciting. So a little pause on why it's important to teach systems thinking, just because it's a term that not many people are aware of. I only heard the term systems thinking on the second year of my PhD, and it became the main topic of my research and teaching, so there you go. So chemistry education and engineering education, there is wide recognition now from top scholars that we have to pay attention to systems thinking, and we have to teach it to students, including in the undergraduate level. So one very simple way of looking at technological systems, and this is very widely accepted and published, is what's called structure, function, and purpose. So what is the system, what does it do, and what is it for? That's a technological system, right, in a nutshell. Unlike a natural system. So if we look at, for example, the water cycle or the carbon cycle or the nitrogen cycle in nature, there is no quote-unquote purpose that we are aware of in the realm of science, of course. If we go to the realm of religion and faith, it's a different story, but if we are in the realm of science, scientific inquiry, we don't really say that the purpose of the water cycle is to provide water to human beings. It could just well be to deprive them of water when the water evaporates, right? Or whatever it is. But instead we say the outcome. We don't say purpose, we say outcome. How does it affect things we care about? That's a minor, not a minor, it's actually a major difference between the two. But you can still talk about structure and function quite easily when it comes to a natural system. So this is a working definition of systems thinking, and it's specific to engineering education because there is a big difference. However, it does also apply, for example, for experimental design and science. So if you're a scientist, you're doing engineering design when you are creating your experiment, right? So the skill or the ability to identify, or a whole research program even, not just experimental design, right? If you have like a 10-year, 5-year research program, you're effectively designing something. So the idea is that you want to identify, understand, predict, and improve every aspect of the system, outcome, function, structure, behavior, and so on, how they relate to each other, and the way they relate with other systems on its boundary. So if you're able to do all this stuff, you're an expert systems thinker. But you start with just understanding the aspects. The trouble is, and this relates directly to my topic of research and teaching, I am more and more focusing on early year education, like first year and so on in undergraduate studies, and specifically with systems thinking, but it's not just a case of systems thinking. I believe it's also to do with problem structuring and other skills to solve unstructured problems. There is a lack of frameworks, pedagogical frameworks, which are suitable for developing and assessing those skills. Quite often, if we do assess those skills, we use a completely different type of framework and a different type of theory than what we used to teach them, which doesn't really work when you think about it. It should be appropriate for novices, kids who just finished high school, basically. It should be domain agnostic. So whether it's within engineering or within natural science and so on, because unstructured problems by their nature are multidisciplinary. If they're specific to a discipline, then they're no longer really an unstructured problem. So it has to be domain agnostic to some degree. It may not be applicable to everything, but within a number of disciplines. And finally, it should be scalable and adaptable to various learning objectives. So if the professor or the instructor cannot actually use these because it takes too long to learn and too long to train, or it takes too long to do the assessment, or it's too complicated for the students, or it requires some specialized equipment, that doesn't really work for what I do, because I want to provide wide application. So this is a framework that I've published and I work on, which is specific to first-year education. It's called SAFO. It's specific for technological system, but it can actually apply to any artificial system. So a university, for example, right? Or a social technical system like a rail network. So technological systems, we look at architecture, which is made up of structure and behavior. We look at function, which has to do with control, input, and output. and we look at outcome. Problem, stakeholders, benefit, and detriment. And I'll explain what that means. So the system architecture is asking what is the system? Mechanics, hardware, software. Okay? So no people, basically. So we want to look at parts and how they relate to each other. And we want to look at the causal relations, cause and effects, interactions between parts. This makes up the architecture. Then we have the function of the system. What does the system do? And how does it interact with systems on its boundary that it's touching with? So you have input systems, you have control, systems that control our system, and we have output. And this can be the same system. You can have a system that's input and control, or you can have two input systems, right? But these are the things you need to think about when you think of a function. So you can see that this is going a level up, right? The system function is, in a way, the architecture of these multiple systems, essentially. It's the same idea. You just say, okay, my system is one part. This system is another part. Now, how do they relate to each other? How do they interact? And the next level, which is sometimes neglected in engineering education, not always, but we tend to focus a lot more on architecture and function, or what I call architecture and function, and less so on outcome, which is how does this actually affect people? And especially, how is the system I'm developing that is meant to solve a problem or fulfill a need for a group of stakeholders, what detriment is it going to cause? What damage is it going to cause, and to whom? Because any system that operates in the real world is going to cause some kind of a detriment. It's going to extract resources, or it's going to cause pollution, or whatever it is, right? How do we mitigate for that? How do we choose between one value and another? These are questions that scientists and engineers do need to ask themselves, and they will eventually need to ask themselves, once they finish their undergraduate degree, even if they go to graduate school and so on. Once you start interacting with the real world, these questions come up. So systems thinking is in this framework is understanding each one of these components, but also understanding how they relate to each other. How does the architecture lead to the function? How does the function lead to the outcomes? So I'm showing you an example based on one of the two solutions my students came up with in my project-based course. Remember Ulaanbaatar, the hot brick, replacing the coal. So this is one of the solutions they came up with, is kind of a trolley inspired by scissors, actually. And the idea is that the gears have a fence usually around them. This is actually a picture from the countryside, so there's no fence, but usually there is a fence around them. And there is a little hole for trash, for garbage. So the idea is that they'll have this trolley, which is very simple and cheap. They can keep it inside the gear, and the brick will be on it, like in a stove, and it will release the heat. And they can, when they go to work in the morning, they can take the trolley with the brick. When it's cold, it's already cold, they put it next to this hole, and then delivery person will come outside of the fence, take out the cold brick, put in the hot one, they come back from work, they take it in. Now, of course, you need like an insulation box because there's like an hour in between that it's left outside and so on. But you can see how you can take this solution and put it in the framework I just showed you, right? This is the architecture. This is how it's going to function with this other system, right? The person is another system. And this is the outcome, is that we are taking care of this family so they're happy and healthy and so on, right? They don't have to use coal. So now you can use this to do formative assessment as well. So again, we want to teach our students how to approach unstructured problems. This is not something that has to go on their transcript, on their grades. The idea is that we want to give them these skills, and we want to check that they have these skills. So we want to use formative assessment. We want to look at what they said the architecture was, how they described the function, how they described the outcome. And for each one, we want to check two things. Did they understand the framework? What I just explained to you, did they understand how this works? But is it also correct? So when they explain the architecture, when they explain the function, is it actually correct or not? For that, you need domain expertise, right? And based on each one, you can now give them pointers, and you can say, okay, it's usually done as a team, not individually. You can say, okay, team, you did very well on architecture. but not so well on, say, the detriment, like what potential damage your system can cause. You need to think about it a little bit more and come back to me with an answer. So this is it for my presentation. As you can see, there's a very long list of references, and you're welcome to check them later. I also publish articles on Medium. I don't know if you know Medium. It's kind of like a blog platform. And they are shorter and more digestible and maybe a bit more fun to read than some of the academic papers. So, you know, if you don't necessarily want to become a super duper expert on all this stuff, you can read those and maybe find them useful. And I'll be very happy to take your questions. Thank you for listening. I'll just get some water, sorry. Yes, please. If you have any questions whatsoever, I'll just pull up the contents again to remind everyone what it is I was talking about.
Hello, hello.
Hi.
Hi again. My question is the next one. In our case, we are trying to apply all this to physics, right? And to physics lectures, I don't know, maybe laboratories. But in your opinion, is there any proposals that you maybe have or that are being applied in MIT in order to teach physics in another way? Because we usually don't have that much freedom, and laboratories are also very algorithmic. So at least for me, I can't see in this moment how could I apply all this to physics.
That's a great question, and it's a great question because I have a prepared answer. That's always the joke when someone is presenting. It's a great question because I have an answer. So I had to think about this for the workshop, right? Because the workshop is going to be for physics faculty and instructors, so it has to be applicable to what they're doing. Or, I mean, I think certainly for applied physics, it's very, very useful. What I would say is, and this is actually what I had planned for the workshop, is to focus on case-based learning specifically. Because in case-based learning, the problems are still quite well structured. There is a spectrum even within case-based learning, which we will learn about today. But case-based learning is good for two reasons from what you brought up. One is that the problems can be more well structured. The second one is that it doesn't have to take as long. So you don't have to change your entire course. You can just say, okay, I'm going to take 1 week or 2 weeks out of my course to do one case-based learning module. Now, specifically, how are you going to teach your specific topic? That's exactly what these workshops are going to be about. So the first workshop is going to be what it's like as a student. I'm going to give everyone the same case, and each team is going to work on the same exact case, and we're going to go through the entire process, presentation, evaluation, and everything. And the second day is going to be, okay, now you can create your own case-based learning module because you know what it's like to do it, you know what it's like to assess or evaluate the results. But yes, generally I would recommend case-based learning and also potentially inquiry-based learning, which is also here. But inquiry-based learning takes a lot longer, so you will have to change a lot of things in your course. But inquiry-based learning is used a lot in science education. So it starts with a question. It doesn't start with a case so much. So just to explain a little bit more for those who won't be in the workshop. So case-based learning originally came from medicine and law. And if you know this idea, med students, sometimes the university hires actors, real actors, to come in and play as if they have symptoms of some disease, right? And they come in and you interview them, and then you have to figure out, okay, what disease, what is the diagnosis, what would I treat them, and so on and so forth. So it kind of came, and in law as well, it's kind of a similar thing. You have cases, right? And you have to find out, okay, what law applies here, what law applies there, what different interpretations are there. But as of the last 20, 25 years, it's been used a lot, and again, as I said, especially in biology education. There are examples from physics. They're not numerous, but again, I would say the easiest thing to start with, if you've never done active learning and you want to try out and see what it's like, is case-based learning. And you can use some of this maybe as inspiration, I'm not sure, but you know, these are all 2 weeks, 1 hour every week, 2 hours they work outside of class. They've never encountered this before, and I'm joined by a subject matter expert who knows about whatever it is we're talking about, and I created each of these challenges or cases with them. So this is like a general answer, but I would say case-based learning is your, and then you can read more about it, you know, not necessarily from me. You can go online, read more about it, see how it can work for you.
More questions? No? No? All the questions are
Great.
are going to be on the workshop, maybe. Okay,
Yeah,
let's
very
thank the
good.
speaker again.
Thank you.